Okay, so today we have with us David Rotz from the University of Toronto. He's going to be presenting some work on tracking, which will be presented at ICML in a couple weeks.
Thank you. So the work I'm going to talk about today is called Combining Discriminative Features to Infer Complex Trajectories. I'm currently a PhD student working with Rich Zemmel at the University of Toronto, and the other co-collaborator was Simon Ossendero, one of Jeff Hinton's postdocs. So the problem I'm going to address today is that of fitting a probabilistic model to a set of continuous state variables, and we're going to try to estimate these state variables from a sequence of observations. So this is stated kind of abstractly, but a more concrete example might be trying to estimate the location of a basketball, which is a continuous variable that evolves over time, given high-dimensional observations, which are the video sequence. You could imagine applying this to some other settings, like robot localization. In that case, your state is the true position of the robot over time, and you have various sorts of observations. For example, information from the odometry, how far the legs or wheels have moved, locations of visual features which might suggest where the robot is, or maybe audio cues. So if you notice that the radio has moved, the sound of the radio has changed, then you might get some indication of where you are based on that. So the trick to this approach, we're going to model this as a discriminative conditional model, which is a little different from how people usually do it. And this has a couple of advantages over the typical generative state space models like Kalman filters and HMMs. Basically, this allows us to pile on features. So if we can come up with any way, any sort of feature that might suggest where, what this continuous state variable is. So the running example I'm going to use is my friend Simon bouncing a basketball, and then we'll watch him tracking the ball later. So any features which we have which might suggest where the ball is in this video, or then we can add them to this model, and any sort of features that describe the dynamics. So our understanding about how this continuous state sequence might evolve over time. We can throw all of these in, and then using labeled training sequences, we can learn which features are relevant. And more than that, as we're tracking, so when we're using this at runtime, we can learn or decide which features are useful and switch them on or off dynamically. So include all the features you want, learn which are relevant in a training session, and then online you can switch them on or off depending on whether or not they're relevant at a given time. So if you know a lot about machine learning, then you might think this looks a lot like a conditional random field, except that we have a continuous state variable instead of discrete, and our features can switch on and off. And then if you know a lot about the stuff that Jeff Hinton's group does, then you might say this is a product of experts, except that we're training it conditionally. So the motivation here. The standard way of modeling continuous state sequences given observations is using a generative state space model. So here, if we have a sequence of observations y and our state sequence x, then we model it by using these two components. First, we have an observation likelihood that says what do the observations look like given the state. So what is an image like if we know the position of the basketball? And then we set up a prior distribution p of x, which describes how this state sequence evolves over time. So how do we imagine the ball flies through the air and bounces? Then you take these two probability distributions, you apply Bayes' rule, and out of it you get the posterior distribution, p of x given y, which is your estimate of what the state sequence is given your observations. So this standard approach, like a Kalman filter is the canonical example, has a couple of quirks. First, to make this computationally tractable, you have to assume conditional independence of observations. That means that given the state sequence, all of the observations are independent. And that is generally not true, because if you imagine, I know the position of the ball, then the two images at nearby fractions of a second in time should look very similar. I mean, they'll have correlated features not related to the position of the basketball and such. So this is more or less a simplifying assumption that makes things computationally tractable and works pretty well in the real world. And then the other quirk is that you have to use a single likelihood function to model the entire high-dimensional observation. So your generative process here, your P of y given x, is what does the image look like given x is our position of the basketball. And so it's very complicated. You have to basically learn some way of modeling the entire generative process of, basketball at position 10, 12, and then generate an image of my friend Simon holding the ball and bouncing it and doing whatever it should be. So it can be very difficult to create these likelihoods. Instead, our approach, which have been taken by others, but we're applying it to continuous sequences, is to model this posterior distribution, P of x given y, directly. So this has a couple of advantages. First, we don't have to make the conditional independence assumption. Because we're always conditioning on the observations, we don't have to assume they're independent. And any features we use which might help us determine where the ball is can look at more than just the observations at one time step. So our features can look at windows of 5 time steps, so 5 video frames, or can look at, say, the whole image sequence when trying to determine where the ball is. So this allows us to use much more complicated and interesting features. And the other advantage here is that features can be discriminative. So a way to think about discriminative versus generative. If you had a generative likelihood, then that would be like me giving you a location of the ball and saying, I want you to draw a photorealistic image of Simon bouncing the basketball. Whereas if you had a discriminative feature, it would be more like me handing you a picture of Simon with the ball and saying, give me a rough idea where you think the ball is. So, I mean, in many cases, the second, discriminative features, could be a lot more easy to create. And this framework gives us the other advantage of allowing us to include any sort of features we might imagine, and then we can learn their relevance. So if there are any questions, feel free to stop me, or if there's anything that's fuzzy about the math or statistics, then just let me know. Okay, so what are features? In this model, I'm going to include 2 different kinds of features, dynamics features and observation features. Dynamic features consider the state at 2 adjacent time steps, at xt minus 1 and xt, and they return a value indicating how well do these 2 states match. So if we have some notion about how the ball should move, how likely is it that these 2 adjacent states fit, say, the ballistic trajectory of a basketball? This will return a large value if they match well and a small value if they don't match very well. So, for example, this could be, if you knew about linear or nonlinear dynamics, it could just be, do these 2 states match according to this dynamical model? And then the other sorts of features are observation features. So these ones take the image sequence or observations and give a guess as to what the location of the ball might be. So so this, in principle, could be any sort of appearance model or object detector. So if you have some black box that takes an image and spits out a guess as to where the ball is, maybe based on color or shape or any one of those things. Now, one novel aspect here that we're adding in with these features is the ability to robustify these features by switching them on and off. So if you're throwing in features at any given time, they might be on the ball or they might be giving spurious results. And to keep those from polluting our estimates here, we're going to introduce hidden binary switch variables. So UJT is binary, and it's 1 if the dynamics feature J is relevant, it's on at time t, and 0 otherwise. And VKT switches the observation features on and off. Yes?
How do you decide whether it's relevant? How do you decide that when you want to switch a feature?
Well, so for example, the observation features each give a guess as to where the ball might be. And if several of them agree, then you imagine that they're right. So they're all firing at the same location. They're all saying that the ball is there. So it's sort of a weight of evidence. We have two sources of evidence, this agreement. So if the dynamics agrees with the observations, then probably all those features that agree are right and should be on. And then I'm going to get to it in a little bit. We include extra side information that allows us to determine, based on the observations, whether we think certain features should be on or off. So we'll get to that, and if you're still uncertain, ask me. Okay, so probability model. If you're good at parsing factor graphs, this is what this looks like. I can probably skip past it. So if you like probability instead, I'm going to build up the probabilistic equation that we use here. So if you're just looking at features, then this is just a standard log linear model. We're taking the exponent of the sum of all of the dynamics features across all features in time, and all of the observation features at all times in. And so you can think of this as a log linear combination, or as a product of all of these features, like a product of experts.
What independence are you assuming there? Because it is a product. It must be, you're treating those features as sort of as pseudo probabilities, right? And then
right.
Taking the product.
Yeah. So we are making the Markov assumption in time.
Okay.
That each state is related to its neighbor, and we don't have. Yeah. And I think that's the only independence assumption we're making, because we're conditioning on the observations at all time. So we're not making any independence assumptions with the observations in state. Yeah. So if you want to see my slides later, this is the factor graph, and you can figure out all the independence assumptions from this. Okay, so this is the basic model, and this is without switching features. So if we include the switches here, then we just add an extra variable that multiplies by each of these features, and if it's 1, it turns it on, and we pay attention to it, and if it's 0, then it switches it off. And then the final addition is these side information. So basically, if your features are unreliable, then switching them on or off at the correct time will dramatically affect your performance. If you know which features to pay attention to, even if there's only one that's right, and you know that that's the right one, then you can do well. And if you're not sure, you pay attention to people who are giving you bad suggestions, and you'll do very poorly. So to improve the ability of our switches to turn features on and off, we're including additional information. So these guys, these calligraphic F and G, are just saying we're going to look at the observations and get to some indication as to whether or not this feature should be on or off. So you can think of this as some sort of classifier that looks at the observations and tries to guess whether these should be on or off. So in this one in particular, we're just using logistic regression, so like a linear classifier that looks at certain information. So for this one, the observations, it's easier to understand. If you're using an appearance model, so for example, a template of the basketball, and then you scan it all over the image and you find the one location that it matches best, then you can compute the error with which it matches the template matches the image. And this error, you can use it and combine it in a linear classifier to indicate whether or not this switch should be on or off. So if the template matches well, then that's strong evidence that this switch should be on. And if the template matches poorly, then we should probably ignore this feature because it just isn't very likely to be the basketball. So the switches are determined by this information. Does it agree with the state sequence? Does it all fit? And this side information features that we use to give it a little boost. Okay, so the features in more detail. So specifically in this model, we're going to use these sort of Gaussian energies or Mahalanobis distance features. So for each, let's start with the observation features. We're going to have a function that looks at the images and at time t tries to predict where the ball is. And then the feature is just the negative sum of squared distances weighted by this precision term or inverse covariance matrix beta k. Similarly, with the dynamics, we have the state at the previous time, then some function here that says how are we going to evolve this, how are we going to take it one step forward according to dynamics. And in this particular instance of the problem, we're going to use linear dynamics here. So we're just going to move it forward according to some notion of linear dynamics. And then we're just going to compute the squared error between the state at time t and if we evolve it forward one step. And then again, we weight it by this precision matrix alpha. So the precisions alpha and beta are the parameters that we're really interested in setting well when we're learning. They're what indicate how reliable a feature is. You can think of this as a covariance in or Gaussian if it's inverse covariance. So if it's very large, then we have a great deal of confidence in estimates by this feature. And if it's very small, then we don't really pay attention to this feature much because it's very noisy. So in learning, we're going to try and set these alphas and betas, and they say whether feature j or k is reliable. Side information. So I mentioned this before. We need to include some extra features to help decide if these switches should be on or off. And we're going to use basic classifiers here, so logistic or softmax regression. So in particular for the observations, we're going to look at the errors with our observation models, our appearance models, and that will give us our indication if we should turn them on or off. Okay, so unfortunately in this model, what you want when you're trying to estimate your state sequence or track is this distribution, P of x given y, the continuous state series given the observations. And obtaining just this distribution is actually quite hard. The reason for that is that we have all of these binary switches. So P of x given y is actually P of x u v given y, and then we have to marginalize out over all the different possible settings of our switches. And because they're binary, we have exponentially many. So doing inference is difficult. But unfortunately, fortunately, we have two things that we can leverage to make a fairly easy approximate inference scheme. First of all, we know that P of x given the switches and the observations is easy. So if we know which features are on and off, and we have the image sequence, then we can estimate the states very easily. So this essentially amounts to something like Kalman filtering. You're just going to do expectation, so a forward pass of a belief propagation, what the state should be, and then a backward pass. And then you can come up with an exact version of this function, P of x. And then similarly, P of uv given xy is also easy. If you know the state sequence and you know the observations, then you can tell which features were telling you the right thing. So you can tell if the switches should have been on or off because you already know where the ball is. So these two things are easy. So P of x given uvy, you can infer using belief propagation. And these switch probabilities, you can sample or compute their probabilities using these simple things. So this is just a sigmoid function of some linear terms, and this is just a softmax. So these are both easy. Now, to put this together, our inference scheme is going to be, if we're given an observation, we're going to come up with some initial guess as to what the switches should be. So we can look at these classifiers we had earlier that will tell us whether these switches should be on or off, and they're just kind of a weak indication. And then given those switches, we're going to do inference to get the particular state sequence. So we're going to apply this guy and get an estimate of x. Now given y and x, we're going to re-estimate and resample the switches u and v. And then we're going to take this new series of u and v and get a new version of x by sampling. So this is sort of an iterative Markov chain Monte Carlo scheme for sampling from this distribution. So we can use this to compute expectations, the expected sequence. So learning. The goal of learning here is a supervised training of these precision, these inverse covariance terms that I indicated before. And this is to train the precisions of the features, so how reliable are certain features. The algorithm that we're going to use is contrastive divergence by Jeff Hinton, which is basically an approximate gradient descent scheme. I'll skip the details of that, but I can refer you to information if you're interested. If you know a lot about Jeff's Boltzmann machines, then you can think of our state sequence as his visible units and the switches as his hidden units. Now, in addition to learning these precisions, we can also improve the quality of our side information features, so these classifiers, which are suggesting if switches should be on or off. We can just sort of wrap this learning into the gradient descent and do it all at once. So from some initial guess as to what these parameters should be, we're going to refine them. Yeah, if you want to see the gradients, this is what they look like. They're kind of messy. Okay, so a quick recap. What are we doing? So we're building a probabilistic model of the state given the observations, and we're posing it as a log linear combination of dynamics and observation features. The way we set it up, you can include any features you'd like, and you're going to learn which features are precise and which aren't from labeled training data. And then when we're tracking at runtime or doing inference, we're going to dynamically switch features on or off depending on whether or not they're useful. So the application, I did pose this in a general setting, but tracking is the application we've been aiming at here. Our goal here is to estimate the location of the ball based on some unreliable observation and dynamics features. So here our state sequence is at each time a 6-dimensional vector that encodes the position, velocity, and acceleration of the ball. And our dynamics features are going to be linear dynamics. Our observation features are going to be some sort of detectors that try and guess the XY position of the ball only. So an interesting thing to note here is that features don't have to say everything about the state. So these observation features, they're only going to predict X and Y position. So their precisions might be high for X and Y precision, but they're not going to say anything about velocity and acceleration, which is also part of the state. So they're going to have essentially 0 precision in those predictions. So this is a way of combining features that give different sorts of information, so they don't have to all say everything about our state vector. So we're going to train this model using video labeled with ground truth. So I took some of the sequences and labeled where the basketball is in each frame. It can be rather tedious, but so we've got sequences of video images and the ground truth locations of where the ball is. And then in our ground truth, I've just filled in the velocity and acceleration using finite differences. So we train this model, learn the precisions and these switching features, and then run it on these sequences. So what observation features are we going to use? My goal here was just some features that I could code up quickly that give a rough indication of where the ball is and really aren't that reliable. So these ones that I threw together in like an afternoon start with 6 templates. So from the training data, I fit k-means, did k-means clustering on images of the basketball, and came up with 5 templates of what the ball should look like. And then I also randomly picked one of the frames and took out the image of the basketball and added that as a template. So each of these features, at every time step, we just scan this template over the whole image, and we find out where it should be, and then the guess of that feature is the one location in the image that has the lowest matching error between the template and the image. As a somewhat more reliable model, we trained principal components analysis using only 3 components, and this was again on images of the basketball from the training sequence. And we use the same deal here. We scan it over the whole image at each time frame and return the location that has the lowest reconstruction error. And then our final feature for the observations is local background subtraction. So this is the only one that actually uses windows larger than just a single frame, but we're looking at adding more complicated features right now. So this one, we take a window of 5 observations, and then we, so these are images, and then we just take the mean of it, and then we subtract that from the image at the current time step, just to get an indication of where the most motion has occurred. And so we're going to come up with some spot on the image where it's changed a lot. So if only the basketball is moving, you can imagine that this might be a pretty reliable indicator of where the ball is. But if there are other things moving, like the player is moving or the camera is moving, then this feature is going to be terrible. Linear dynamics, we're going to include 4 different dynamics features, and these are just the standard physics that you get for a ball in flight, a ball bouncing off the ground, a ball bouncing off the wall, and just sort of a Brownian motion, sort of a random dynamics for when the player is holding the ball, because we don't have a good a priori notion of how the ball is going to move. Our side information, again, is reconstruction error of the templates. How well do they match? Okay, so now it's time for videos. So in this one, we use the first 500 frames labeled with ground truth to train, and then we're tracking on the remaining frames. Here, the blue indicates where the ball is, and at each time step we have a circle. The diameter of the circle is our uncertainty there. It's like a plot of the covariance in our estimate. The red and yellow dots are locations that the observation features say are most likely to hold the ball. So yellow ones are observation features that we think are relevant and we've switched on, and red are observation features that we think are terrible and we've decided to switch off. So you'll notice that these features are, at any given time, there's probably 1 or 2 on the ball, but a lot of them are terrible and they're just giving us very unreliable results. So we're able to track the ball through, despite using these very poor observation features. So in that video, we do lose track of the ball 4 times. Twice of them it's because the ball is occluded. Simon holds it behind himself, and so it's a legitimate loss of track here. And then twice it's because we incorrectly switched features on or off when we shouldn't, and that screwed up our estimation of the state sequence. We compared it with 2 other trackers. One is the previous work I did on an incremental learning PCA tracker, and it can track the sequence up to frame 688, after which it fails and it can't recover. And then we also applied the mean shift algorithm, and it basically has no traction here because it relies on color, and with this low contrast ball it can't do anything. So here are some highlights from the video, or lowlights as the case may be. Here's where the ball is hidden behind Simon, and we incorrectly determined that these features should be on when really they're not indicating where the ball is, so we get lost there. But as soon as the ball reappears, so this is just a few frames later, then we notice it and the state sequence estimation corrects itself. This frame is an indication of the importance of the dynamics features, so we're not just doing some sort of detection at each time frame. At this case, there are no features on the ball. The only ones that are on are incorrect. Yet because they don't agree with the dynamics, so I guess this estimate is worse than the dynamics, then we stay on the ball because we're not being fooled by this misinformation. So this is just some diagnostics about exactly what we learned here. This is a plot of the standard deviation of each of the features. So I said before we learned a precision matrix for a diagonal precision matrix for each of these features, an estimate of how reliable it is. And so I just inverted it and took the square root to get this standard deviation. And so this is units of pixels in the image. So we see here that the principal components analysis feature is the most reliable. The k-means templates are slightly more reliable. The single image that I just randomly picked is not too bad either, but this background subtraction is way out. So it doesn't give a very reliable estimate as to where the ball is. So this other graph over here is an indication of how often the features are actually on the ball. So if we look at the ground truth, we can see, how reliable is this feature? When was it right? When was it wrong? And then these two lines are the true indication of whether it was right or wrong, and this is our estimate. So how were we right at deciding if this should be on or off? So you see for most of these, we're very good at deciding when features should be on or off. But this one feature here, we're very bad. So this background subtraction, my measure of whether this feature is right or wrong, it's just, did it give a location, an estimate, within 5 pixels of the true location? So this background subtraction feature almost never gives a location within 5 pixels. So it should be off all the time, yet we're turning it on almost all the time. So if you put these two pictures together, you can figure out the reason. Basically, this feature is unreliable, so we've downweighted it. So we're not paying too much attention to it anyway. And although we have it on all the time, its predictions are very noisy, so we're just we're keeping it around because it's sometimes in the neighborhood, but we're not paying too much attention to it. So the first example was simple in that we were doing weak generalization. We trained on a sequence, on the first part of the sequence, and then tested it on the remaining part of the sequence. So as a further experiment, we're going to train on 2 different sorts of sequences, and then train on a separate one, or test on a separate one that we've never seen before. So here we have 2 training sequences, one where Simon and my advisor Rich are rolling a basketball back and forth, and another where they're bouncing it back and forth. And then our test sequence, they're going to be either rolling or bouncing at the same time. So in none of the training videos have we seen both rolling and bouncing. So this one's a little slow. They're just rolling the ball back and forth. Again, red features are ones that we're switching off, and yellow that we think are on. So the first 500 frames of this was used for training, as well as the first 500 frames of the bouncing sequence. And then for the test sequence with rolling and bouncing, we didn't train on that at all. This is the other video that we trained on. So we trained on the first 500 frames, and then this is just the result of tracking the whole thing on its own. So I think the one yellow feature that's giving a lot of spurious results is the background subtraction or motion detection feature, and we're not paying too much attention to it. Okay, I lost track there. Okay, so this is the test video that we'd never seen before. It actually does a little bit poorly at the beginning here, but this illustrates the main failure mode of this algorithm. If you have unreliable features and you're not able to tell that they're bad, that you shouldn't pay attention to them at a time, then we're going to make mistakes. So there are features here firing on the back of this Toyota there, and we're not able to turn them off. So it just makes mistakes at the beginning, but then near the end it's more robust. And here we're combining 2 different sets of dynamics, and we didn't see both of them in the same video before. So in terms of initialization, in contrast with a lot of trackers where you have to, give the ground truth location in the first frame, you have to click on where to start. This one doesn't need initialization. And because of that, it can recover when it gets lost, which is something that a lot of trackers, including my previous work, didn't do. Okay, so as a further experiment of this, we tried applying it to the problem of occlusion or missing data. So as a final sequence, we used the tracker that we trained on rolling and bouncing, and we applied it to the problem of tracking the ball behind this recycling bin. So as you'll see, Simon throws the ball, goes behind the bin, and then it reappears on the other side. And for this short segment, we're able to track it through both of these occlusions. And we use our knowledge of dynamics to estimate where the ball should have been, roughly, as it goes behind the bin. So you'll notice that it doesn't perfectly follow the ball as it goes behind the bin, but I think that's because we don't have, it's hard to estimate that the ball has bounced when it's occluded. So one of our further pieces of work is to try and be able to do that. So in terms of related work, this is a lot like many different methods out there. The most closely related is work on conditional random fields by Lafferty and McCallum. You could think of this as a conditional random field with a continuous state space and more complicated features. This is also related to products of experts and to exponential family harmoniums, which is work by Max Welling at UC Irvine. The generative analog of this, so the standard way of doing this would be switching linear dynamical systems, which a lot of people are using in tracking, such as people at Georgia Tech. And then there's also mixed state, continuous and discrete particle filters. I think this is work by Andrew Blake. I think switching linear dynamical systems and mixed state particle filters are essentially the same thing, except you're using MC-MC in the second one. There have been other people who've done discriminative trackers related to ours, like Christian Smincescu. But his work is related to estimating body joints, and he doesn't do the same sort of learning framework that we do. Another very similar thing would be a Kalman filter with input gating. So this is in standard computer vision textbooks, basically a Kalman filter, and at each time step there's a classifier that picks one of the observations and says which one it's going to pay attention to. So what are we going to do next? In terms of the features that we're using for tracking, this is pretty much just a prototype. These features are very simple. We threw them together quickly. So we're interested in using better features that are more reliable and use more of the observations. So one thing we're considering is optic flow. We can use this in the framework because we have all the observations. So we can do optic flow over more than just one time step. We can do it over larger time windows. And we can use that to indicate maybe which features should be on or off. In terms of observation features, we're thinking we could use SIFT features, or at the very extreme, each feature in our model could be the prediction of another state-of-the-art tracker. and we can learn which of these state-of-the-art trackers are reliable at given scenarios, and when we can switch them on or off to decide what we're going to do. Another interesting another direction that we're exploring right now is including different modalities. So I just have observation features here, which are based on the images. But when the ball bounces behind the bin, a good indication of the fact that it has bounced is the fact that you hear the sound. So we're looking at using sound features to try and give us indications about what the dynamics should be. Important to moving this to more interesting domains would be using nonlinear dynamics. And we're also interested in applying this to other data. So my colleague thinks that we get rich if we manage to apply this to financial time series. But robot localization might be a more realistic problem. And I'm open to any suggestions that anyone might have as to problems that we could apply this to. Okay, so that concludes my talk. Thank you all for coming.